So first of all, I would like to thank everybody for the invitation. This is the first time I give a talk as part of this New England thing, and I would like to encourage you guys to keep doing it because it's really a fantastic event. So I'll be talking about papers to appear, which means that if there's anything wrong in the talk, hopefully you can correct it and fix it in the paper.
We're responsible.
Right, you're responsible. With Clay Cordova, Dan Fried, my fantastic student, Hotat Lam, and the paper is to appear. So as an introduction, there's a long history of papers studying quantum field theory, classical field theory as a function of its parameters. And I'm not going to give any references or description of the history here because it will simply be way too long. And there are typically two classes of applications of these. And as we go through the talk, you will see that these two different views on the same topic will come again and again. One is we vary the parameters and we view the theory as a function of the parameters, not just as a fixed value of the parameters. We make believe that we have a dial or a knob that allows us to change it, and that can lead to vary phases and so forth. So this is one application. And the other application is that I can make the coupling constant space-time dependent and view, say, a massive fermion, but as a function of position-dependent mass. So this is a question that is a valid question to ask in quantum field theory. And these two are different aspects of allowing us to change the parameters. One, we change in space-time. The other, we keep the parameter in space-time fixed, and we gradually change and review a multi-parameter family of theories. And you will see how these two views will end up being complementary to each other, and they will both be useful. More generally, we should view every theory as a function of the space-time dependent coupling constant. This is the most general thing we can do. If we have a global symmetry, we can couple it to a background gauge field. This is classical. So when I mean background theory is classical. And I would also like to put the system on an arbitrary geometry. So for small infinitesimal changes, there are, say, the symmetry is U1, I can consider correlation functions of the current. But that can be thought of as giving an infinitesimal expectation value, an infinitesimal value to a background U1 gauge field. That's what turning on a current means. But I can also consider the system in the background of a magnetic monopole, and that cannot be found by just exponentiating the current. This is a more subtle observable, and we ought to understand all of that. Similarly, the system on various space-time geometries, the spin structure, etc. And all of these are important even if we are not, imagine we are some condensed matter experimentalists, we are not interested in studying our laboratory on RP4, because our laboratory is not in RP4. Yet putting the quantum field theory on RP4 can teach us something about its behavior. And we'll see examples later. And part of that is to explore defects. So we can take the background gauge fields, or the metric, or the position-dependent parameters, and let them vary in space-time, and that's what's called a defect. A defect is not an excitation of the system, but we put the system in the background where the parameters vary in space-time. For example, we take a four-dimensional fermion, it has a mass, and we can let the mass depend on the xy plane, and have its expectation value wind around infinity, and we'll later do this particular example. So what we'll discuss is something which we'll call generalized anomalies in this large space. So we consider the theory as a function of background gauge fields, background metric, spin structure, whatever geometric thing we want to put, and that's a new element, as a function of position-dependent coupling constants. And we compute the partition function of this whole thing, and we'll see that there are anomalies there that are visible only because we included, so there are anomalies there that have nothing to do with the coupling constants, they're kind of independent of the position-dependent coupling constants, but there will be new anomalies associated with the fact that the coupling constants can vary, and I'll give examples. And for me, this is extremely satisfying because I think it's of the order of a dozen different papers that I've written over the last few years are all compressed to one simple expression in terms of this new perspective. And I'll demonstrate it later. So this will streamline, unify, and strengthen many known results and will lead to new ones. So the way I'll do that, I'll start, so I had a challenge here, how to present that. We've studied a lot of examples. I don't have a general answer, but we've studied a lot of examples. Some of them are more interesting because they address kind of state-of-the-art questions that we would like to think about, systems that we don't know what the answer is. But we also have a lot of simpler examples, say in quantum mechanics, that demonstrate the same phenomena. So I had a conflict. Should I present the interesting, dramatic examples? Or maybe what I should do is focus on the simple quantum mechanical systems, where on one hand we can solve the system, and on the other hand, we can use the fancier formalism to address it. And the danger of going this second route, well, the advantage is it will be more pedagogical and more fun. But the danger is it will look completely trivial. Here is a system that we can solve, say, the harmonic oscillator. Why should we address this fancy formalism to analyze it? It would not be the harmonic oscillator, but there would be other such simpler systems that are completely understood. Why do we need the fancier formalism? It's kind of overkill. So we'll have a trade-off, and I'll start with that. And Cesar says these examples are elementary. This formalism is not really essential, but it would be a pedagogical way to proceed. And then I'll briefly turn to more advanced and more recently studied examples. And finally, we'll end, depending on how much time I have, we'll revisit the free fermion in 4 dimensions. I don't think we'll quite connect to Daniel's talk, but you will see why I was on top of some eyes there. So, as I said before, anomalies have 2 classes of applications. One is the one-parameter family of theories, and the other is the defects. And in the class of multi-parameter family of theories, we learn like 2 various constraints about the long-distance behavior of the theory. So Tuf told us that we analyze the system in the UV, we find some anomaly, and then the infrared behavior should exhibit the same anomaly. And now we're going to play this game with these new anomalies, and we'll see that we can predict phase transitions at long distances due to these new anomalies. So that would be the first application. And the second application will be the study of defects. We'll study some defects, and the discussion of the anomaly will tell us something about the dynamics along the defects. So we'll have a cosmic string, and the cosmic string will have to have massless particles on it because of these anomalies. Now, since, as I said, this view really unifies a lot of known results, so I assume that many of you will say, first of all, some of the examples are kind of completely trivial, we don't need the formalism. And the rest, people might be familiar with the answer and say, oh, we knew it all along. I searched the literature very carefully, it's not in the literature. So it might be that one aspect or another look familiar. The new point here is not this new aspect that is familiar, but the overview that we do all of them at the same time. So let me start very pedagogically with one of my favorite theories. This is a quantum mechanical system, exactly solvable. This is a particle on a ring. So the Lagrangian is q dot. So q is the degree of freedom, identified with q plus 2 pi. And the Lagrangian has a kinetic term, q dot square. And we put a theta term, theta q dot. And this system is exactly solvable. And we diagonalize the Hamiltonian and we find the spectrum. This is the spectrum. And the spectrum is 2 pi periodic. The system has instantons. When q winds around Euclidean time, that's always an integer. Gives here an integer, and therefore theta and theta plus 2 pi give us the same answer. And we see it also in the spectrum. This is the spectrum of the Hamiltonian. But we already see something very peculiar. This formula is non-invariant, and the theta goes to theta plus 2 pi. But the full spectrum is. So as we shift theta by 2 pi, the spectrum is rearranged, and the state n goes to the state n plus 1. This will end up being the basis of our anomaly. The fact that the spectrum goes back to itself, but the states are rearranged. What are the symmetries? There's a U1 symmetry. We can shift q by an arbitrary constant. We have symmetry which we can call Ct. C because it flips the sign of q and reverses the sign of time. This is the symmetry for any. And when theta is 0 or pi, we also have charge conjugation, just q goes to minus q. This term is obviously invariant. This term is not. It's odd. But the theta equals pi, it maps pi to minus pi, and we already said the theta is 2 pi periodic, so this is a symmetry. In these two transformations, U1 and this charge conjugation combine to O2. Now, in a paper a few years ago, we showed that theta equals 0, the Hilbert space is in an ordinary representation of O2. But the theta equals pi, the Hilbert space is in a projective representation of O2, because it's something that can be interpreted as a mixed anomaly between charge conjugation and U1. I'm going to rederive this result without ever using charge conjugation. This would be the main point of this talk. But at theta equals pi, this system has level crossing. Remember, if you just look at the spectrum, the state n equals 0 and n equals 1 have the same energy at theta equals pi. And therefore, there is level crossing at theta equals pi. And these two states, why do they degenerate? Normally in quantum mechanics, we don't have level crossing because levels repel. Here, the states are degenerate because together they form an irreducible representation of a central extension of O2. So this is straightforward quantum mechanics. And if you have to teach quantum mechanics in your class, I strongly encourage you to teach this example because it demonstrates it has a lot of features that I have not yet mentioned here. It's really beautiful and it's completely solvable. Let's consider it a little better. Well, we have a global symmetry which is coupled into a background U1 gauge field, A. So A is an ordinary U1 gauge field. It's classical. And wherever we see Q dot, we simply write Q dot plus A. We also allow to add what we can call a counter term, another term that depends on A, but depends on A only. So it does not affect any correlation functions at separated points. And this is like fancy Chern-Simons term. It can be thought of as saying that shifting the charge of the Hilbert space by an integer k. Now we see something peculiar. If we shift theta to theta plus 2 pi, this term doesn't change. Here the term with Q dot doesn't change, as it didn't change before. But the coefficient of A is shifted by 1. That means that if we allow this term, the space of coupling constant is larger. It includes theta and an integer k. But the system is not quite 2 pi periodic. Because when we shift theta by 2 pi, we get the same system only if we also shift k by 1. Otherwise, the system with the background field is not invariant just shifting theta by 2 pi. We also need to shift k. Physically, the statement is essentially what I said before. The spectrum is invariant. The U1 charge of each state is n. And if I shift theta to theta plus 2 pi, the states are rearranged. And since the states are rearranged, the charge of the state n is mapped to the charge n plus 1, which has charge bigger by 1. And that corresponds to shifting k by 1. Now, we could say that I really like that theta is 2 pi periodic. Because the original problem has 2 pi periodicity. And I also like the U1 symmetry. So one option is to choose a value of k which is half integer, then I sacrifice the U1. Or I sacrifice the 2 pi periodicity of theta. But I would like the system to be 2 pi periodic for arbitrary a. And one way to do that is to add a bulk term like that. So this already smells a lot like an anomaly. We have conflicting requirement. One of them is the U1 symmetry, and the other conflicting requirement is the 2 pi periodicity of theta. We cannot have both of them, and either we sacrifice one or we sacrifice the other, or we add a bulk term. These are the typical 3 options with an anomaly. We either have one symmetry or we have something else, or if we want to have both, we have to couple to a bulk, and then there's dependence on more bulk. So the new thing here is that it's not the U1 symmetry that is anomalous and not charge conjugation, but instead the property that is anomalous is the 2 pi periodicity in theta. Once we understand that, we can start changing the system. So the first thing I do is break the U1 to Zn. For example, I can add a potential. Now the system is no longer solvable. If I add a potential, the system is no longer solvable. But the qualitative conclusions are unchanged. For n even, there's a similar C with Zn anomaly at theta equals pi, and hence the ground state is degenerate there. For an odd, there is no such anomaly, not a projective representation, but there is still the degeneracy of levels at theta equals pi. And there are various ways to see that. In that case, we can choose this counter term, the value of k, such that the Zn symmetry is preserved and the charge conjugation is preserved, but it's not the same one that was used at theta equals 0. This is the first time in the talk that we use anomalies to find a new result. It's not that deep, but a result in quantum mechanics that we couldn't just solve by finding, but just by diagonalizing the Hamiltonian, because we can't diagonalize the Hamiltonian. It's more difficult. Yet we know that at theta equals pi, there should be a degeneracy. I'm going to derive it differently. I'm going to modify the system even further. So before we had charge conjugation at theta equals pi, and we had U1. Now, first we said, let's get rid of the U1 and have just Zn. This picture remained the same, but we could solve it. Now I'm also going to remove C. So I'm modifying the system. I add another degree of freedom, x, a real coordinate. I couple it to Q dot in this fashion. So it's add Ix Q dot, and with a generic potential. So this is a well-defined quantum mechanical system. 2 degrees of freedom, Q in the circle, X is real. This is the Lagrangian. This system does not have the U1 symmetry, nor does it have charge conjugation for any theta. So all we have is Zn. So we're going to solve this system. Well, we're not going to solve it explicitly, but we'll still say something non-trivial and a bit surprising about it. So the claim is, so what we'll do, or the way we'll analyze it, we add a background Zn gauge field, A, and add this, our favorite counterterm, which is k is now an integer modulo n. And again, theta is not quite 2 pi periodic, the same argument as before. If we shift theta by 2 pi, k should be shifted by 1. And now we see what happens. Is we shift theta by 2 pi, the states are rearranged, the same as before. So if we started, we track a state with Zn charge n, and we change theta by 2 pi, it becomes a state of charge L plus 1, modulo n. So what that means, if at theta equals 0, at theta equals 2 pi, we have the same spectrum, and the states were rearranged. That means that somewhere along the way, states had to cross. That's surprising, because at the point, first of all, different states can cross at different points. Second, normally states in quantum mechanics don't cross unless there is a symmetry that guarantees the degeneracy between them. Now there is no symmetry that guarantees the degeneracy between them, and yet they cross. So we get levels that cross without a symmetry between the two states.
Wait, how do you know they cross?
Because the spectrum at theta equals 0 was this. I don't know what it is, some spectrum. And these states, each of them is in some Zn representation. At theta equals 2 pi, the spectrum has to be the same.
Yeah.
But what I called the trivial Zn, imagine this was a Zn, trivial Zn representation, it went to this. This state went to that. So somewhere along the way, I don't know where, the two states had to cross, and they couldn't mix. Normally in quantum mechanics, when you have a situation like that, this crossing becomes this, right? The levels repel. There will be small interaction done. In this case, this does not happen. It does not happen not because these two states are related by a global symmetry, which is the famous way we avoid level crossing, but instead, these two states have different charges, and they have to be degenerate because they start this way and they end up that way. So we can say that there must be a phase. So if we just track one state, this is what a phase transition is in quantum mechanics. The ground states cross. So if you compute the ground state energy as a function of theta, then necessarily is a phase transition, somewhere in the middle. So there are two views on the parameter space. As I said before, theta k is identified with theta plus 2 pi k minus 1. This shift by minus 1 here is the statement about this background charge that multiplied, the fact that the charges here differ by 1 from the charges here. So what we say that either theta is not identified with theta plus 2 pi, but by 2 pi n, and then the Zn symmetry is preserved. Or we say theta is 2 pi periodic, but the ZN symmetry is violated. And this is a generalized anomaly between the ZN symmetry, and they're related, not in this system, related discussions in an unpublished work by Thoringen and another paper that Chikawa, Yonekura, and I wrote on this different topic. And this clash between them, this anomaly, can be removed if we add this bulk term. So regardless of how you describe it, there is an anomaly between the phenomenon of 2 pi periodicity of theta and the ZN global symmetry. That's all I use. I don't need star conjugation. I don't need the U1. And that anomaly is the formal way to describe why there must be level crossing. I also gave an elementary explanation of why there must be level crossing, because states with different charges have to be rearranged. So they had to cross somewhere. So I gave an elementary explanation, and I gave the fancier one using anomalies. And in the more sophisticated examples, I will not have the elementary one, but I will have the more sophisticated one.
For the elementary one, it was important that the ZN was not broken, so that you could meaningfully talk about the charts.
Not explicitly broken.
Huh?
That's correct. I needed the global symmetry.
Yes.
I needed there's no spontaneous variable.
Right. I
needed
meant
the
global symmetry.
So the anomaly I have is a mixed anomaly between the ZN symmetry and the 2 pi periodicity. These are the two facts, and we cannot have both. So either we have one, or we have the other, or we add bulk terms. That's the fancier language. Physically, what it implies is that there must be level crossing. We'll soon see more. I'll go a lot into this example because there are many lessons, and then I'll do the more sophisticated ones faster.
Sorry, Nadia, can you just say what went wrong with, so the naive argument for theta periodicity is you say that theta is multiplying q dot, and
Yeah.
q dot is periodic?
Yep.
So.
This is still correct.
Okay, but then if that's the only place that theta appears in the path integral, then it sounds like it should be periodic.
It is periodic. The answer at theta equals 0 is the same as at theta equals 2 pi.
Okay. How about
But-
at theta equals
but-
pi and theta equals minus pi?
Still the same answers.
Oh,
Whatever
okay.
you compute at theta is the same as at theta plus 2
Okay,
pi.
that's what I thought.
But the observables are relabeled. The whole thing is about the fact that the observables are relabeled. So if you sit at 1 theta, it's no anomaly.
So even if I turn on the background gauge field?
Then
for-
it's easier to see. If you turn on background gauge field, the system is not 2 pi periodic.
Yeah, so can you say what's the additional term? Sorry, you said
Yeah,
it, I'm
I
just
will.
trying to, can you write it, the action with the background gauge
Yeah.
field? You have it somewhere, but.
Here, so this term is not.
Oh, I see,
invariant.
it's just that term, okay,
Yeah.
fine, yeah, fine.
So if you set A to 0,
Yeah, of course, yes.
but if you add this term, the symmetry, and if you have the ZN symmetry, you still have an analogous term.
Of course.
So what we have here is a mixed anomaly between the ZN and the 2 pi periodicity. But that means that each of them separately, there's no problem with each of them separately. Just if we try to turn on enough backgrounds. So one way to think about it, as I said, every anomaly has two classes of applications. One is the dynamics as I vary the parameters. So as I vary the parameters, I argued that there's necessarily a phase transition, the point where the levels cross. We derived it, gave an elementary definition, but we also gave a fancier one. So viewing it as a one-parameter family of theories, the anomaly means that there must be level crossing. And as I said, alternatively, it follows from tracking the ZN charge of the ground state.
Can you call this a -1 form symmetry?
They will soon be there. They're very smart. I think it's the next slide.
Oh, okay.
No, it's after the next one. Yes. The other application is we can think of it as an interface. I talked about defects. So I can imagine, so here we have only time, so it's a little bit degenerate, but I can consider the system as theta varies as a function of Euclidean time. So I'm going to do this dichotomy. I either call theta fixed in space-time and consider a family of theories, or I let theta vary in space-time and find something interesting when theta varies. So we'll soon do that in detail, but in order to do that in detail, I have to define the action a little bit more carefully. So this will be a little bit more technical. So we would like to know what we mean by this when Q and theta are not functions on the real line, but functions to a circle. So there's no problem, yes?
I'm sorry, I'm going to take us a little bit back. The point of this bulk term, should I think of that as like a best amino effective action QCD, the thing that it takes care of the fact?
No, exactly. Good question. It's not. The West Zumino term is independent of what you do in the bulk. So you didn't have to do it. It's convenient to do it, but you don't have to. Here, the bulk term is such that the answer does depend on the extension, and which is characteristic of anomalies. Thank you for asking. So if the Q dot term is well defined, but the theta term is not well defined, because if theta is a map to the circle, or space-time circle is mapped to theta, which is a circle, and specifically if theta winds around, this is what we're going to get mileage by theta winding around in the circle, then what do we mean by theta Q dot? So that needs a more careful definition. The more careful definition goes with patches. Just divide space-time, the Euclidean circle in this case, to patches. In each of them, theta is well defined in R, so I can just integrate. But the rule is that whenever theta jumps by 2 pi m on the transition functions, I add by hand this term. And the reason this is a good thing to do is that, first of all, it is independent of the trivialization. If I move the places where I cut, I'll get more or less contribution from here, but this will be compensated by a contribution from here. That's something you can easily check. It is invariant both on the periodicity of Q and on the periodicity of theta. And we also see that if theta winds around m times, this term will tell us that the answer is not invariant on the shifts of Q by alpha. In other words, forget the U1 gauge field. Somebody asked me before, who asked me about turning on the U1 gauge field? I think you did. Imagine you didn't know about turning on U1 gauge field. I don't do that. But I consider a configuration where theta winds around the Euclidean circle. So as I move around the Euclidean circle, theta moves by m unit. This thing violates the global U1 symmetry by m units. So we see here the clash that if theta winds around, then the U1 symmetry is actually violated. I don't need the background U1. So, which is again one of the hallmarks of anomaly that we see here. So we can study 3 kinds of interfaces. Here it's still kind of degenerate because all we have is time, so it's not really an interface. We later have an example where this is in space. First of all, we can let theta vary in a smooth way. And since it's smooth, it's clear that the answer is universal. This is something which is included in the formulation of the theory. I can also have a discontinuous jump. Then it's not universal, and at that point I can add an arbitrary operator here. Now finally, this is what I said before, if theta jumps by 2 pi m, and I put a specific operator, e to the I m q at this point, this interface is transparent because the shift, imagine you shift that a little bit, and the integral on one side, you integrate less theta, the difference in here, but you add e to the imq here minus e to the imq there, and that exactly cancels using integration by parts. So an interface like that is a transparent interface. So let's imagine we have such a smooth interface, and we make it very steep. So we just vary theta as a function of time, Euclidean time in this case, from 0 to 2 pi m, and now I make it very steep. So in quantum mechanics, if you look at your quantum mechanics books, there's something called the sudden approximation, where you evolve with some Hamiltonian, and then you very rapidly switch to another Hamiltonian. So here we evolve up to here, so let's use this approximation, and we have a bunch of states, and now we have another Hamiltonian with theta shifted by 2 pi m, and we said that instead of shifting theta, I can just relabel the states. That's what the shift of theta is. So I relabel the state shift every n to the state n plus m. In terms of wave functions, it's clear that I multiply by each wave function by e to the I m q. That's what it means to shift the momentum by m units. And that means that the interface carries charge m. In other words, we see here that along this region, where theta varies rapidly by 2 pi m, it is as if we have an insertion that violates the U1 global symmetry by m units. So now we come to what Daniel already smelled. This stuff look a lot like a symmetry. We'll later see an example where that's not the case. But in this case, we can think of it as a symmetry. So normally, an anomaly is associated with a global symmetry, zero-form symmetry, one-form symmetry, and so forth. With the charged objects, for zero-form symmetry are particles or local operators. For the one-form symmetry, the charged objects are strings, and the charged operators are line operators, etc. Now, we can think of these anomalies associated with a minus one-form symmetry. Now, a minus one-form symmetry is not a symmetry. Just as a minus one brain is not a brain. A minus one brain is an instanton. It's not a brain, an object in space-time. Right? It's a point. And in fact, if you use duality, what looks like an instanton in one frame is not an instanton in the other frame. But yet, we can loosely, we can actually make it a little bit more precise. We can think of what we have here, this 2 pi periodicity of theta. We can think of it as a minus one form symmetry. So we can view it as a global symmetry. Theta is the gauge field. It's not well defined because we can shift it by 2 pi. So theta is the gauge field. Ordinary gauge fields have one index, AU. This has 0 indices, so because the symmetry has one, it's a minus one form symmetry. And d theta is like the field strength. It's well defined even across interfaces, across overlaps, as we know. And then this anomaly follows the standard picture of anomalies where we added something like a Chern-Simons terms in the bulk, which was theta dA. So if you take this point of view, then it looks a lot like ordinary symmetries. Let me move up in dimensions and discuss a two-dimensional U1 gauge theory. So gradually the examples will be more and more sophisticated, less and less solvable, but we'll use the same technology. So we consider a U1 gauge theory with n charge 1 scalar fields, and we have arbitrary potential. I don't even care if all the phi's are massive, or there's a potential that gives them an expectation value, and then it becomes a nonlinear sigma model. And I can also throw in all sorts of other neutral fields that's not going to make a difference. And we include the theta term, and we are not going to assume charge conjugation as is normally assumed in the discussion of this system. So we make a very complicated system. And the system has a global symmetry, SUN, that rotates the different phi's. But actually, the global symmetry that acts faithfully is PSUN, very similar to the way Daniel modded out by Z2 in the previous talk. Here, the center of this SUN does not act on gauge invariant things. Now, as always, when we have a global symmetry, we turn on background field, B. And now we have freedom to add a counter term. This W2 is the second Stiefel-Whitney class of the PSUN. The details are not important. There's another integer we can add. And again, theta is not quite 2 pi periodic. Theta is not 2 pi periodic. We had theta. If we just have this term, we would say that theta is 2 pi periodic because it multiplies instantons. But now we are smarter. We turn on this background field, and we have this k, this integer that we add in the action. And as we shift theta by 2 pi, k goes to k minus 1. This is the basis of a Nobel Prize in physics. The Holden chain is a demonstration of this phenomenon. This is well known, although not quite in this description. And in this paper, we gave this description of this anomaly. So this can be viewed again, and so the fact that there's this identification was given in the paper, and now I'm describing it as an anomaly. As an anomaly, so in this paper, we tried to use that together with charge conjugation, but now as I forget, we don't even need the charge conjugation. All I need is the conflict between this global symmetry and the 2 pi periodicity. This is enough to drive the show. So this can be viewed as a mixed anomaly, again, the same thing. And it's described by such a three-dimensional term, where, again, we have d theta and this W2. The details are not important, but the story is, again, the same. Either we preserve the periodicity in arbitrary background, or we preserve the ability to add arbitrary background, or we add a three-dimensional bark term. So now we're going to use this anomaly in the same way we used it in quantum mechanics. And as always, we have two classes of applications. One of them is a one-parameter family of theories, and the other is defects. So in the first one, we have a one-parameter family of theories, the system is gapped. So we have a gapped system. So if we stay at low energies, something at low energy, we change theta. Something at low energy should reproduce the same anomaly. Right? This is what the TÜV told us. Whenever there is an anomaly, a low energy observer should reproduce it. But if the all the low energy observer sees is one state, and now we crank theta bigger, there is no way the low energy observer can reproduce the anomaly unless somewhere, at some value of theta, something happens. Something could happen. That means there must be a phase transition. And in previous treatments, this use charge conjugation symmetry. Now we don't even use a symmetry. We can have whatever you want, and we predict that as we vary theta by 2 pi, there must be a phase transition somewhere. The second application, as always, is to consider interfaces. So now I'm looking in space. Here is my space. It's a 1 + 1 dimensional system. And I vary theta in space. So theta is constant. Then it changes, say by 2 pi m, and then it continues constant. So if I'm here very far, I see theta is a multiple of 2 pi, is the same as 0. If I go very far here, theta is also a multiple of 2 pi. It is another multiple of 2 pi, say 0. So physics should be the same. The anomaly tells us that that's not the case. An electric charge is localized on the interface, and specifically, because of the anomaly, we see that the interface is in a projective representation of PSUN. Its anality is M. And physically, this is something that Coleman already knew, that if you want to change theta by 2 pi, you produce particles out of the vacuum. You send them out in order to screen the charge. And in the place where theta varied, the charge goes there and it sits there. And we have M units of charge there. So this morning, Zohar described a related phenomenon, but not in this language. So here we see the whole thing just because of this anomaly. So these two things you could derive without the anomaly, but it's nice that they are all coming together using this anomaly. I'm moving to 4 dimensions, and as I move up in dimensions, it's getting more and more abstract. Now we are in the SUN gauge theory, pure gauge theory. It has a ZN one-form global symmetry. This is the statement that we can study the system not with SUN gauge fields, but in PSUN gauge fields. There are more bundles we could study, but we do not sum over these new bundles. We specify them. So now that means that we can couple the system to a 2-form gauge field B, Zn valued, and that 2-form gauge field specifies the second Stiefel-Whitney class of the twisted SUN gauge theory. This is something that the TÜV introduced. This is called the TÜV twisted boundary conditions. We do not sum over them. We take the original SUN theory and we put it in some twisted boundary conditions. This is an observable in the SUN theory. This is not something that we sum over. Unfortunately, there is huge confusion about this in the literature. But this is a property of the SUN theory. And we can study the SUN theory as a function of this background gauge field B. And again, we have an anomaly. As we shift theta by 2 pi, there's a counter term I can write, B, and that term is called the Pontryagin square. The details are not important. If I shift theta by 2 pi, this term does not come back to itself. Since it does not come back to itself, we have a mixed anomaly between the Zn one-form symmetry and the theta periodicity. And it can be described by this 5-dimensional term. So very much like in the previous story, we have a conflict between the global symmetry and the theta periodicity. And that conflict, either we sacrifice one or we sacrifice the other, or we specify more data how the theory behaves in 1 dimension higher. Now, using this understanding, we can derive a lot of results in the literature. In fact, some of the things that Zohar talked about this morning are trivial consequences of this. He talked about some sheets, and he said that there's something interesting in the sheet. So he said that there's an eta prime particle that winds around, but instead of saying that eta prime, that is dynamical, winds around, I can just study the theory without eta prime, without matter, and let theta wind around, because eta prime is a lot like eta prime is a lot like theta. So we view the system as a function of theta, no quarks. We let theta wind around, And as such, we're going to have interfaces. Or we are going to view the system as a one-parameter family of theories and derive that they are phase transitions. And if I sound like I'm repeating myself, this was intentional, because I want to show you that we study many, many systems, and it's now like a machine. You have a system, identify the anomaly, view it as a one-parameter family of theories, identify the phase transition. Go back, study the interfaces, and we are going to do that now. So one application is if we add fermions in the adjoint to this system, the system becomes n equals 1 supersymmetric. And here there's an anomaly between the Z2n R symmetry, there is ordinary zero form R symmetry, and again the Zn one form symmetry. And this anomaly means there are domain walls. So the system has n ground states, and there are domain walls between these ground states. These are domain walls where theta jumps by 2 pi across the domain wall. SUN n equals 1 in 4 dimensions has n ground states, and you can move from one to the other by changing theta by 2 pi. There are various ways to see that. And this mixed anomaly means that there must be something non-trivial on the domain wall. And something non-trivial is a topological field theory, which figured also in Zohar's talk this morning. So there must be a topological field theory, and it's the same topological field theory that Achira and Vafa found using some string construction. So when they did it, they had it for the first time, they found this topological field theory. It wasn't clear to me whether this is a result due to the field theory or due to the string theory that it was embedded in. Now it follows from an anomaly in the field theory. And instead of thinking of this anomaly, we could have done the same thing just with this symmetry. So if somehow somebody takes the SUN theory with n equals 1 and add the operator to break the R symmetry completely. We don't have the R symmetry, it's gone. This anomaly will still guarantee the same thing. So this topological field is even more robust. It does not need most of the symmetries that go into the discussion. Another application without SUSY, we have a mixed anomaly between time reversal, or equivalently CP, in the Zn one-form symmetry. So this was used in this paper to show that the theta equals pi, there must be, or elsewhere, there must be a transition. And the transition, which is believed to be a transition where CP is spontaneously broken. Again, that figured in Zohar's talk this morning. He said that the theta equals pi, or when eta prime equals pi, there are two ground states, and the system hops from one to the other. And that follows from a mixed anomaly between CP and this one-form symmetry. Now we say the same thing is true, even if we don't have time reversal. So imagine we take the same SUN gauge theory, we add another scalar field with this coupling, and very much like what we did before in the quantum mechanics system, and add some dynamics for phi, and let it all be very strongly coupled. So we don't have time reversal symmetry, we don't have CP, yet this anomaly exists, and it guarantees that this phase transition takes place.
Matthew, all your examples involve, so far, are something varying in one dimension, so you can also think about levels crossing and so on. So
No, here it's not level crossing.
Sorry, but... Yeah,
But you're right about one dimension, but if you wait, the next one is in 2 dimensions. So it's really fun to give this talk because the questions are about the future, not about the past. So we have a non-trivial topological field theory on the interface, and we can, in this case, so this was analyzed in this paper and then elaborated on in a recent paper, and we discussed various gauge group, SUN, PSUNs. In the new paper, we'll write SPN and SPN and all sorts of variants of it. So just to recapitulate, we'll have 3 kinds of interfaces. Now we move in space. This is a field theory, not the quantum mechanics example I had before. So if it's a smooth transition, this is an observable of the quantum field theory. We vary theta in a smooth fashion. So if we know how to solve a quantum field theory, we should also be able to solve it as a function of position-dependent theta. If the change is discontinuous, then it's not universal because there is freedom to add more degrees of freedom living only here. Now, if we jump by precisely 2 pi n, and we put specific degrees of freedom here, specifically it's a Chern-Simons term, then this interface is transparent. So it's very much like what we did in the quantum mechanics. As we go higher up in dimensions, I promised you it would be more subtle and I will go faster. but it's very much like what we had in the quantum mechanics. This is a special case of that where we squashed it. Then we could add more things. And then with a specific thing, this thing is actually transparent, and this is the periodicity in theta. Now, my colleague asked me about 2 dimensions. So here it is. Actually, for years, I was looking for examples of systems that have not a 1 cycle in the parameter space like theta, but theories that have a 2 cycle in the parameter space. And I wanted it for all sorts of esoteric reasons. And Morrison and Donaghy found examples which were based on quite esoteric field theories. These were the 0-2 theory on a Riemann surface, and as you vary the parameter, the moduli of the Riemann surface, which appear as parameters in the 4-dimensional theory, there are 2 cycles, closed 2 cycles, which led to all sorts of puzzles, and the puzzles were resolved partly in this paper that I mentioned with Yonekura and Tachikawa. But now I'm going to present another example with a 2 cycle. And fortunately, it's a lot easier. We don't need 6 dimensions. And we do not need this Riemann surface and the 2-0 theory. We just take a free theory, a free massive Weyl fermion in 4 dimensions. So the parameter is 1 complex mass m. The theory is free. There's nothing else to change. And I'm going to add the point at infinity. And if I add the point at infinity, I'll have to check whether I can really do that. I can imagine the parameter space being a cycle. A mathematician might not like this definition, but what I'm going to do is ask what happens as I vary the masses on the complex mass plane, and I will also study interfaces where the mass covers the entire xy plane. So we need to do both. So the first thing I'm going to ask is what happens is right at infinity, there's a whole circle, which is the phase of m. So I could say, aha, I have a fermion, let me rephase the fermion and get rid of the phase of m. So if I shift the fermion by a phase, multiply it by a phase, I will relabel the mass, and I could say, the mass is always real. I can take the mass to be real and positive. But that's not quite right, because there's a gravitational anomaly. So if I'm performing this rotation, then the Lagrangian is shifted by a term proportional to R wedge R. So in this case, this is the analog of all these counter terms I had before. So remember, in the quantum mechanics example that coupled to a background U1 gauge field, big A. In the 4-dimensional example, I had a 2-form gauge field B, and its terms were shifted by periodicity of theta. Here, it's the metric. So if I rephase the fermion in order to get rid of the phase of m, then this term that I add to the Lagrangian is shifted by this amount, and 192 is correct. So what does it mean? It means that we can add a gravitational theta angle to the system. So our system is a fermion, which is dynamical, coupled to classical background metric, with this coupling with R wedge R, and there's a gravitational theta parameter. And now we label the theory by a complex mass m, a gravitational theta parameter theta g. This depends only on classical fields. And if we relabel the masses, we relabel m by a phase, we shift theta g by alpha. So the equations look very similar to what we had before. We had a parameter that couples to the dynamical fields. We had another parameter that couples only to classical background fields. And when we go back, we change something that brings us what appears to be like the same point in the parameter space. The coupling to the background field is shifted. So we are not quite at the same point. So this is the hallmark of the anomaly, that as we vary m, we vary the phase of m, then the Lagrangian is shifted by this term. So now it looks like an anomaly, and we can tell the same story again. So this is the identification. So for non-zero m, we can remove the anomaly by absorbing it in a redefinition of the gravitational theta. So we could say, we have m, we thought m is in the complex plane, but I can rephase it and let m be real and positive. But then theta g will be redefined this way. However, we cannot do it for all complex m, because this is problematic at m equals 0. So as long as I stay away from m equals 0, there's no anomaly. I can reshift, I can relabel things and get rid of the anomaly, but not at m equals 0. So only when I look at the whole complex plane simultaneously do I see the problem. And here is your two-cycle view. So we can write the anomaly term in 5 dimensions. It's a gravitational theta term times some delta function of m, d to m. The details are not important. You can also write it as a 6-dimensional term. And there's a related discussion about 2 cycles in a paper I wrote with Tachikawa and Yonekura that I mentioned earlier. So the upshot is that we are in exactly the same situation as before. Namely, we have an anomaly between various identifications in the common constant space and something we would like to preserve. In this case, it's gravity. So before we had it with the global symmetry, we had an example where the anomaly was with the 0-form symmetry and the 1-form symmetry. Here it's with gravity. So what are the applications? So now I sound like a broken record. I guess the younger people in the audience, or most of them, don't even know what a broken record sounds like. You know, there was this thing that was rotating. If it had scratches, you would hear the same thing again and again.
It's not too broken, actually, you know.
You're completely right. Scratch record. See, I don't even remember the phrases. So option 1, it's a 2-parameter family of theories, and what the real and the imaginary components of M. So at some what this thing tells us, at some point in the complex M plane, the theory cannot be gapped because it was gapped at infinity. As I move around infinity, I shift by this R wedge R term. So the same thing should be true as I shift in and in, as I move inward. But if the system is always gapped, this cannot be the right answer because something will have to give as M gets small. Now, in the case of the free fermion, it's obvious. The fermion becomes massless. The point where the fermion is massless, we recover that. But we can take this system, or cousins of it, and couple it to all sorts of other interactions, gauge fields, scalars, have it strongly coupled, and so forth. Take the mass very large. The rest is not important. I move around infinity. I find an anomaly. Now the system is gapped there. The anomaly tells me that as I move inward, somewhere, I don't know where, but somewhere, something will have to give, and there will have to be new degrees of freedom, or there should be a phase transition. So somewhere in the interior of the M plane, the system will not be trivially gapped. So there must be some transition. So this is the first class of applications. Note we don't have any global symmetry. So we take a system that depends on the mass. The system is gapped. It's arbitrarily complicated. We vary the mass around infinity. We find this anomaly. And this tells us that somewhere at some value of the mass, everything else stays fixed. At some value of the mass, the system, there has to be a singularity. Namely, there must be some new massless particles. Might be interacting, but something will have to be there. The system cannot be trivially gapped for all M. So this is the first kind of application. The second kind of application is defects. So it's the same machine again and again. So imagine I pick the xy plane and let M wrap the xy plane. So let M be position dependent. It winds around infinity. Imagine I take coordinates x and y, and M is proportional to x plus iy. So this means that there is a string along the z-axis. And exactly this string was analyzed by Jaquiv and Rossi. And what they found in our language is that the anomaly means that there are Majorana-Weil fermions on the defect. This is, of course, closely related to the Cullen-Harvey, the famous Cullen-Harvey phenomenon of cosmic strings, which led to superconducting cosmic strings. But these examples, A, involve some Higgs fields, which are more complicated. We have it in the free theory, just the mass is position dependent. Second, we can let this system couple it to whatever we want. And as I said, have the interactions arbitrarily complicated. The system is gapped. So this system is gapped. And we don't care what's going on at infinity, near the origin. Just that somewhere at infinity it winds around. We know that not only is the system, so the system will not be gapped somewhere. And not only that, our anomaly tells us that there must be chiral stuff on the interface. And you see it from here. In the first discussion, I varied M M was constant in space-time and I varied it. And I said that is M varied, I had to pick up this R anomaly from something. And that told me that somewhere in the complex M plane, there had to be a singularity. This was this step. So this is a six-dimensional form. So if M is constant in space-time, I use this application. M is constant in space-time, and this is the this anomaly should derive from somewhere in the interior. The other application, I activate this part of the anomaly using the expectation value of M. So I activate this part with a defect. So I say M varies in space-time. I integrate this thing against that. And then I learned that there is an effective two-dimensional field theory with this anomaly. And a two-dimensional field theory with an R anomaly means that it has a gravitational anomaly, and the numbers are the numbers of C equals a half. C left minus C right equals a half. And as I said, the same conclusion in more complicated examples. So I'm approaching the end. I'm way over the end, actually. So these are my conclusions. So to study ordinary anomalies, we couple every global symmetry, classical background fields, and we put arbitrary space-time, spin structure, whatever. We change whatever, we vary the orientation, whatever we want to vary. And an anomaly is a statement that the partition functions might not be gauge invariant or coordinate invariant. This is what anomalies are all about. And we describe it by a high-dimensional classical field theory of the background fields. Now, we are going to make all the coupling constants position dependent and throw them also into the mix. So we have coupling constant lambda, and we make them position dependent. And now we have an action, a partition function that depends on A and lambda. And the partition function might not be invariant under various identifications in field space. And again, this is described by a generalized anomaly in higher dimensions. So the formalism is essentially the same as the ordinary one, except that it does not involve symmetries. So this is very much like before with anomalies. The formalism is essentially the same, but it has nothing to do with global symmetries or metric. It is associated with the coupling constant. Now, we showed two kinds of applications. One is that the anomaly is invariant under a renormalization group flow, and therefore, this is a la 't Hooft. If we compute the anomaly at short distances, we know something that the anomaly should be the same at long distances, and as a result, we learn about some phase transitions at long distances. The second application is we can construct defects either by letting A vary or by letting lambda vary. And then we use the values of the anomaly to find the anomaly on the defect. So these are the two kinds of applications of this system. So we presented examples of these anomalies and their consequences. And I started saying again and again, like a scratched record. And the parameter space was a 1 cycle or a 2 cycle. We showed examples in 1 dimension, in 2 dimensions. We have examples in 3 dimensions. And we also showed examples in 4 dimensions. So we have studied many other cases that I have not discussed. I'm already going over time. So we studied various gate groups, and gate group with quarks, where the analysis is more subtle. But again, we can learn dynamical consequences about the long distance behavior and about such defects. And there are many other cases that we have not yet studied, and I'm optimistic that they will show new subtleties. The good thing is that we turn it into a machine. Right? We don't have to think now. We know what to do, and we just have to go through the various examples. So thank you.
Okay, we have time for a few questions.
Is there a simple example, like even in QCD with massive quarks or something, where so you make the mass way bigger than lambda QCD far away, you make it wind around, and so something cool has got to happen on the inside.
Yep.
Which isn't just that fermion becoming massless, obviously.
That's right.
So,
That's right.
Well, is there an example? Can you give an example for what the cool thing that happens on the
Yeah,
inside?
so let me give an example. So in fact, it would be closely related to the example that Zohar described this morning. Consider QCD with one flavor. The mass is very, very big. So it does not participate in the dynamics. I vary it around infinity. Now, I can remove the mass. In this case, I can remove the phase of the mass around infinity and put it in theta. The low energy theory is the pure gauge SUA. The Pugh gauge SUN is the first order transition at theta equals pi, and no transition anywhere else. This means that in the complex M plane, can you see here? So in the complex M plane, somewhere around negative M is the first order transition. Because as I move around, this is theta, and this is theta equals pi, this is theta. So somewhere here, there has to be a first, this is the same first order transition. I think Dashen was the first to find it. And this is this first order transition that the Pugh gauge theory levels cross. Because the potential is a function of theta, has this theta square, repeated theta square term. So this is understood many different ways. There is no phase transition here. So this first order transition must end somewhere. We don't know where, but it ends somewhere. When a first order transition like this ends at a point, there must be a massless particle here. What's the name of this massless particle? There's only one flavor in the problem. That's the eta prime. So if you remember, Zohar wrote this morning, there was a potential, maybe minus cosine eta prime, plus there's a 1 over n relative to that.
I see. So there's a point where necessarily it's tuned to be massless. The eta prime gets tuned to be massless.
That's right, eta prime square.
I see. Cool.
So somewhere at large n, you know there's a point which it will become massless. This argument shows that it's also true at finite n. So at finite n, we know that there's a first order transition that ends at the point where the eta prime is massless. So this was discussed in the paper with Zohar and Gayotto, Davide Gayotto. So we had this picture with the massless eta prime. And now we can have various interfaces where M does this. So there's a theory on this interface, or we can let M do that. And we can study the theory on the interface, and it has an interesting structure. Now we can take this thing and study it with many flavors. It's getting more interesting. And we can do it for SON gauge group, works as a fundamental. So every one of these examples has more moving parts. The main thing that drives the show, in hindsight, is this anomaly. That's not the way things were discussed originally. We use time reversal and all sorts of symmetries that are not essential. But the cleanest way to wrap all of these together is this mixed anomaly between periodicity of theta and these various global symmetries in the problem. So for me, this is satisfying because I wrote many, many different papers in different number of dimensions with symmetries and this anomaly and that anomaly, and they all boil down to this simple formula. Did I answer your question? More than you bargained for?
Any other questions? Okay, then let's thank Nadi.